So we're going to add the next type of circuit that we're going to talk about. So we've talked about RC circuits, we've talked about RL circuits. Now we're going to take the resistor out and we're going to put the capacitor and the inductor together. So we're going to talk about LC circuits. So the situation for an LC circuit is we're going to start with a charged capacitor. We're going to connect it in series to an inductor, and then we're going to have a switch that we can close. And so initially our capacitor is charged. When we close the switch, the inductor is going to generate a back EMF so that no current flows for that initial instant. Current will start to flow, discharging the capacitor after this initial instant where the back EMF is equal to the voltage across the capacitor. And so if we use our loop rule, again we'll start down here, and so we know that the voltage increase across the capacitor and going from the negative to the positive plate has got to be equal to the voltage decrease across the inductor. And then the one subtlety that's sort of involved in this equation is that we're basically defining the charge as being the charge on the positive plate, so that as the capacitor discharges, dq dt is actually negative, right? That charge is leaving the plate, which means that the current is negative. And so that's why we end up having sort of flipped this minus sign around. And so we end up with this equation here. Well, we know that I is dq dt, and so when I plug that in, what I notice is, again, I get a second derivative of the charge with respect to time plus a constant term, time the charge, equals 0. And we've seen an equation that has this form before, right? So the second derivative of something plus a constant times whatever that quantity is equals 0. Well, that's what the spring and mass system look like. So we said the second derivative of the displacement from equilibrium plus a constant, in this case it happened to be k over m, times that displacement value equals 0. This was what we got when we used Newton's second law to solve for what was going on with the spring and mass system, right? This is just the acceleration. So the acceleration plus k over n times x equals 0 from Newton's second law. And we said, oh, okay, so this is a differential equation. It happens to have a fairly basic solution. Cosines and sine functions are solutions to this differential equation. And so we just picked that the solution for this that we were going to use was that the position of the spring was going to be equal to some amplitude, right, the maximum displacement from equilibrium, times a cosine function. The cosine was going to depend on this angular frequency term, and then we could use our phase shift if we didn't happen to release it from amplitude at t equals 0. You take the derivative of that to get the velocity function, and again that ends up in this form where we've got a negative omega amplitude still times sine omega t plus phi. Well, since these and then this defined omega, we said omega is going to be nothing more than the square root of the constant that's sitting in front of x in this equation. And then we can relate the angular frequency to the period of this oscillatory motion by basically saying that the period is going to be 2 pi over omega, so 2 pi times, and flip this over, and so now it becomes m over k. So the idea is we know that this kind of equation describes oscillatory motion. Described it for a spring and mass system. We know its solution will be sines and cosine functions. We know the period of that oscillatory motion and the angular frequency of that oscillatory motion can be calculated by the constant term sitting in front of x. Well, what that tells us is that what's going on in an LC circuit is we have oscillatory current. Right? So the charge on the plates and therefore the current will also exhibit oscillatory behavior, and we will be able to figure out the period and the angular frequency of that oscillatory behavior by paying attention to the 1 over LC term that sits in front of the charge. So that means that the solution for this equation is going to be that the charge on your positive plate at any time t is given by this equation. So again, this is just the maximum charge on your plate times cosine omega t plus phi. Again, the current, well, that's just taking the derivative of this function with respect to time. That's going to be negative I max times sine omega t plus phi, which again, when we think about what this maximum current term is, it's just going to be omega times the maximum charge. And so I'll have another way to write the current. It's just going to be negative omega times the maximum charge times sine omega t plus phi. Omega, well, we said that's just going to be the square root of the constant term sitting in front of Q. So in this case, that happens to be the square root of 1 over LC, which oftentimes we'll just end up writing as 1 over the square root of LC. And then the period of the oscillation that our circuit's going to undergo is just going to be 2 pi over omega, so this just ends up being 2 pi times the square root of L times C. So all this is just the basic equations describing what's going on with the oscillatory nature of an LC circuit. Now graphically, well, if I graph the charge on the positive plate as a function of time, it's going to look like this. So all the charge is on the positive plate. We discharge to where there's no charge on my plates anymore. Now I'm going to have what was the positively charged plate has switched, so I've reversed the polarity of my capacitor. Then again, that's going to discharge, and then it'll end up going back and recharging with the same polarity, so the plate that started as being positive will end up positive for a second time, and then it'll just continue to oscillate through that pattern. If I think in terms of the current, well, again, there's some maximum value for the current. Initially, that current's 0 because all the charge is sitting on the plate. But then as that starts to bleed off, I'll end up at a point where the current value is at a maximum. That's going to correspond to the point where there's no charge left on the plates. Then as the plates start to recharge, the current will decrease back to some 0 current when my plates are fully charged, and again all I've done is reverse the polarity. So you can see that to go all the way through the period, I've got to go from fully charged plates, fully charged with opposite polarity, back to fully charged with the same polarity I started with. That gets me through one period. And so the same thing's true of the current. I'm going to start with 0 current. I'll end up with 0 current again when I'm halfway through the period and my plates are fully charged again. I'll end up with 0 current again as my period finishes and the plates are fully charged again. So let's continue this analogy between spring and mass systems and LC circuits. So part of what we've basically done is we've said, well, thinking about this displacement from equilibrium, that's now become thinking about the charge on my positive plate initially. The velocity term, that's now thinking about the current. Mass, that's going to correspond to my inductor term, and K, the spring constant, that's going to be 1 over the capacitor. And so when I sort of put these things into the equations, or these are sort of how I've changed things within the equations, and then physically, well, with my spring and mass, I started with my mass fully away at amplitude, as far away from equilibrium as it was going to get, and I let it go. Again, I'm letting it go, so its initial speed is 0. It'll go through equilibrium, where now its displacement is 0, and it's traveling with its maximum speed. It will go all the way over till it reaches the amplitude on the other side. So this is halfway through the period, where again it comes to rest, so V equals 0, and it's at the amplitude again. It's then going to bounce back. It'll go back through equilibrium, maximum speed now pointed in the opposite direction. Displacement is 0, and then it'll finally get back to where I started as we finish the period. So here's speed again is 0, and I'm back at the amplitude I started at. Well, exactly the same sort of thing is going on in my LC circuit. So I start with all the positive charge on this plate at t equals 0 when I close my switch. What's going to end up happening is that the current will basically come off of this plate. I'll end up with a maximum current when the plates have lost all of their charge. Then as the current continues to flow in that direction, it will start charging the plates with an opposite polarity. So now this becomes my positive plate, and it'll keep doing that until the current dies back out again, and now I have my plates fully charged. So this again is halfway through the period. This is the analog to my mass having bounced all the way over to amplitude on the other side of my equilibrium point. Then my plates will discharge again, so the current will flow back in the opposite direction. Again, it will reach a maximum value when there's no charge on the plates, and then the charge will begin building back up on the plates in their initial polarity until they reach a point where the plates are fully charged, the instant where the plates are fully charged and there's no current again. So this is how our spring and mass system is oscillating just like our LC circuit. All right. So we said one of the other things that we paid attention to in our spring and mass system was energy. So the energy within oscillatory systems. And we said for spring and mass systems, we had the total energy, so our mechanical energy was equal to an elastic potential energy plus kinetic energy. And so here was our elastic potential energy term, 1/2 kx squared, plus our kinetic energy term, 1/2 mv squared. This was true at any point in time where we were at some displacement moving with some speed. But we said if you happen to be at amplitude, then all the energy was in our elastic potential energy term, and you got that with just 1/2 k times the amplitude squared. Or if you were at equilibrium where the amplitude was 0, all the energy was now in our kinetic energy term, and so the total mechanical energy was just equal to 1/2 Vmax squared. Well, all we're going to do again is swap. The kinetic energy is going to become magnetic potential energy. The elastic potential energy is going to become electric potential energy. And so for our LC circuits, what we've got is the total energy within our system is just the sum of the electrical and magnetic potential energies. Again, for our electrical potential energy, we said one way we know we can write that is 1/2 q squared over c. So all I've done is just pull out the over c term. So I've got 1/2 times 1 over c. We said that's just like k. Q squared, that's just like x, plus 1/2 L. So our inductance is like the mass term, and the current is now like the speed. And again, this is what the energy is in our circuit at any point in time where you have some amount of charge on the plates and some current flowing through the circuit. But there are sort of the two special cases where I can have all the energy stored on the plates in the electrical field between my capacitor plates, and so that's going to be 1/2 times 1 over c times the maximum charge on the plates squared. Or I can have all the energy stored within the magnetic field within the inductor. Then I can calculate the energy as 1/2 times the inductance times the maximum current squared. So the energy, again, the energy within our oscillatory system works exactly the same way that we were used to seeing energy work within the spring and mass. And so if you think graphically about what's going on here, again, you're going to start, because we're starting with our plates fully charged. So our fully charged plates means that all the energy is stored within the electric field. None of it is stored within the magnetic field. But as we go 1/4 of the way through the cycle, 1/4 of the way through the period, all the charge is now off my plates. There's nothing left on the capacitor, no charge left on the capacitor, so I have no electric field. Instead, all the energy is now stored in the magnetic field because my current is at its maximum value. And again, as the current dies off, as I recharge the plates, the energy switches back from being stored in the magnetic field in the inductor to being stored in the electric field within the capacitor. And so these two things just swap back and forth in terms of all the energy being stored on the capacitor versus all the energy being stored on the inductor, back to all the energy stored in the capacitor, and so on and so forth. So if you want to think about the total energy, I can think of it in terms of either the maximum charge squared over 2c or the maximum current squared times the inductance over 2. So either of those will give me Either of those will give me the total energy within my circuit, as will this. The only thing here is I just have to know both the current and charge values at the same instant in time. Alright, so again, just sort of graphically, what's going on is, well, we're starting with all the energy stored in the electric field because all the charge, our capacitor is fully charged at t equals 0. There's no current. Then we're going to end up swapping. We now drive a current, so there's some energy, right? We have some charge left on the capacitor. We have some current flowing through the inductor. So I have some energy in both the electric field and magnetic field, but as the charge continues to bleed off the capacitor, I end up with a situation where there's no charge on the capacitor, so there's no energy left in the electric field, and all of the energy is now stored in the magnetic field. So here's the situation where I've gone 1/4 of the way through the cycle, and all the energy is now in the magnetic field. Well, the current is now flowing, and so it's going to continue to flow, which means it's going to start to charge this plate positively, charge that plate negatively, which means I'm going to start to store energy back within the electric field. So some of the energy that I had in the magnetic field is going to be transferred back to being energy within the electric field, and that will continue on until I have all the charge back on my plates. There's no current anymore. I've switched the polarity, but from the perspective of energy, I'm halfway through the cycle and all the energy is back stored in the electric field. Well, now it's just like when I close my switch at t equals 0, it's going to start to discharge the capacitor. It's just going to drive the current in the other direction because I have changed the polarity of my plate, so I'll end up initially with some charge left on the plate, some current in the inductor, so some energy stored in both. Eventually I'll get to the point where all the charge is off the plates, the current is at its maximum value, and all the energy is in the magnetic field. Again, that current will continue. It'll start to recharge this plate. Some of the energy will be in the electric field, some of the energy will be in the magnetic field, and that will continue on until, again, finally I have no current in the circuit. My capacitor is fully charged and all the energy is back where I started. So LC circuits are oscillatory systems in exactly the same way spring and mass systems are. And so what you remember from 298 is going to be critically important in terms of conceptually thinking about what's going on within an LC circuit.